When we're talking about circular motion, there's really two types that we can actually analyze. What we've done so far is analyze what are technically horizontal circles, and that means that the circular path the object is traveling on is actually happening in the x plane, the horizontal plane. So that would be things like the car traveling around a turn, because it's not kind of going in a vertical loop, it's going in a horizontal loop. So what we're going to begin to look at now is vertical circular motion, and the same concepts apply. However, the main difference is that the force of gravity plays more of a role in this. When we travel horizontally, the force of gravity always points down. So, like a car going around a curve, gravity points down. It doesn't point towards the center, so we never really have to consider that when calculating centripetal force or centripetal acceleration. What happens when you do a vertical loop, though, is that gravity does play a role, and it's along with other forces as well. Because as we'll see in a second, gravity will act in different directions at different points on the loop. So if we see this roller coaster and it begins to travel through, well, at the very bottom, gravity is pointing down. Gravity is pointing away from the center. Now it still plays a role in the centripetal force, but it's not pointing near the center, towards the center. When the roller coaster gets up the side over here, gravity points down. Again, it's not pointing near the center. It's not even acting in the same plane as the center. Up at the top, gravity points down towards the center. Near the side, it's down over here, not towards the center. So hopefully you get the general idea that it becomes a little bit more complicated because some of these forces, specifically gravity, will sometimes be pointing towards the center, sometimes not. Sometimes you'll consider them when calculating centripetal force. Sometimes you won't. So it can be a little bit daunting when you first take a look at it, but I kind of break it down into three questions, and if you can understand those three questions, then vertical circular motion is not that actually, it's not too difficult. So the three questions that I think are kind of good to know the answer to. The first one, just an issue of safety. How fast must an object be traveling to not fall out of the loop? If you're a plane going through a vertical circle, you would like to go fast enough that your plane does not just fall out of the sky at some point. If you're on a roller coaster, if you've ever been on a roller coaster, you would certainly like that roller coaster to enter with enough speed to get through the loop. Otherwise, you get stuck at one point and hang upside down for a couple of hours, like you probably see in the news every now and then. If it's an older roller coaster and it's not connected to the track, you certainly would not want to fall down. That wouldn't be good either. So the minimum speed you must travel at entering the loop in order to safely have enough speed to get through, that's probably something that's important and worth knowing. All that comes down to that general question we always ask ourselves: what force or combination of forces acts toward the center of the circular path? So what force or forces actually play the role of centripetal force? It's no different than our previous question, but the or combination of forces, that tends to become a little bit more important. Vertical circles tend to have more combination of forces producing the centripetal force. And the last one, this one I think is just kind of good to know. If you've ever been on a roller coaster, you've been driving in a car and you go over a hill or through a loop if you're on a coaster, something like that. There were probably times where you felt like you were heavier than usual, like you really felt like you were getting pushed into the seat, and times where you probably felt like you were a little bit lighter. It kind of gives you like this weird feeling in your stomach. Some people get a little bit queasy. Um, but what actually makes a person feel heavier or lighter when going through a vertical circle or going through part of a vertical circle, as like a hill on the roadway would be? So what actually makes a person feel heavier or lighter, and are they actually becoming heavier and lighter, or is it just a sensation? So those are the three general questions. So let's get right into it so we can kind of take a look. Well, the thing to realize is, as this enters the loop, as this roller coaster enters the loop, we're going to start to analyze the forces that act on it. So let's look at the bottom first. So at the very bottom, I've drawn the forces that act on my cart, and I've drawn the center of the um, path so that we have an idea of which way the centripetal force should be pointing. So hopefully you realize by now that gravity acts down, the normal force acts up, and the centripetal force is just the net force acting towards the center of the path. It's that combination of force or forces acting towards the center. So in this case, the net force acting towards the center, which is the centripetal force, well, the normal force is acting towards the center. Gravity is acting directly away from the center. So these two have to combine to produce a net force towards the center. Now the centripetal force here must be Fn minus Fg, because Fn is towards the center and Fg is away from the center. In general, instead of like up, down, left, right, we will assume anything pointing towards the center is positive, anything pointing away from the center is negative, and anything that in no way is pointing away or towards the center, we just don't consider. So if it's directly on the line of the center, like normal force points up, gravity points down, but it is along the same line as that center, we'll consider both. Since gravity points away, it will be minus. So if I wanted to calculate the centripetal force at the bottom, well, that would be equal to the normal force minus the force of gravity. An important conceptual understanding to have right now is that even from looking at this, the normal force must be greater than the force of gravity. If these two are equal, I get no net force towards the center of that circle, and therefore this cart will not travel in a circle. I need that centripetal force requirement. If gravity is greater than the normal force, well, my net force would point away from the center, and again, I would not be traveling in a circle. You must have a force, a net force, pointing towards the center in order to have any kind of circular motion. So as I state down here, the Fc would be away from the center if gravity was greater, so therefore the normal force must be greater. It's the only way that I get a net force pointing towards the center. And again, that's my centripetal force requirement. So that's what's going on at the bottom. If we take a look at the sides, well, when we're traveling up or we're traveling around, I've drawn in gravity acting down and the normal force from the track that's going to be pushing the cart towards the center. You'll notice in both of these cases that gravity acts straight down. Because it's off center, it's not really fair to say it acts towards the center or away from the center. It's just not really interacting along the plane of the center at all. So we just don't consider it. So the only forces that are on these diagrams that actually are acting towards or directly away from the center is the normal force. There's no other forces. You could have some friction here per se, but again, the friction in this case would not be acting in any way in relation with the center. It just is acting kind of like parallel to the center line, something like that. So the centripetal force, because it's the net force acting towards the center of a path, in this case, that net force, which is the centripetal force, would just be Fn. Gravity certainly is affecting the coaster, but it's just pulling it down. In no way is gravity making any kind of effort to push this roller coaster towards the center. So in this case, Fc equals Fn. Gravity doesn't act along the center of the path. We don't have to consider it when calculating centripetal force. So originally, we did have to calculate it because it is in line with the center. It's pointing directly away. When you consider the sides, it's a non-factor, so we don't have to consider it. If we look at the top, you'll notice that I have gravity acting down, which hopefully you realize. The normal force, the track, right, the cart wants to go this way. Its inertia wants to send it to the left, but the track, since it curves, is pushing it down and keeping it going towards the center. So I have gravity and the normal force both acting towards the center. So that net force acting towards the center is Fg plus Fn. The reason they're both positive is they both point towards the center. So if you have a force pointing towards the center, it will be positive. A force pointing away from the center will be negative. The force is not really in any way pointing towards or away from the center. You don't consider it. So you'll notice really quickly, at the bottom it's Fn minus Fg. On the sides it's just Fn. On the top it's Fg plus Fn. So it can tend to be a little bit confusing, but if you draw the free body diagram and you look at the forces that are acting on that object and the direction they're pointing, it does tend to clarify a lot of this for you. So really quickly, here's a quick example. I have a yo-yo that's being spun counterclockwise in a circle. I want to know what forces produce the centripetal force at the top of the path, at the bottom of the path, as well as at the sides. So I'm going to pause here for a second. I'll pause the video because I'm not going to sit here for a few minutes. That would be awkward for everybody. So I'll pause the video really quickly, and I'd like you to quickly think to yourself, maybe your notebook, try and figure out at the top, what is Fc? At the top, is Fc going to be Fg plus Fn? Is it going to be some other force? Is it an applied force? So what would Fc actually equal? What force or combination of forces would the centripetal force acting on this yo-yo be at the top, the bottom, and the sides? Once you've done that in your notes, unpause the video and you'll have the chance to look at the solutions and see how well you did. If we look at part A wants to know what the centripetal force would be at the top of the yo-yo's arc. Well, if you look at the free body diagram, tension acts down, gravity acts down. So since they both point towards the center, centripetal force would be Ft plus Fg. The tension in the string and the gravity both pulling down. If I look at the part B at the bottom, well, I still have tension pulling towards the center. Gravity pulls away. Therefore, my force, centripetal force, would equal Ft minus Fg, towards positive, away, negative. And a quick reminder, Ft must be greater because the net force needs to point towards the center. If this is not greater than Fg, my normal force is either non-existent or does not point towards the center of the circle, and I lose my centripetal force requirement. Part C, if you look at either side, in this case, gravity acts down in both cases. In no way is it really acting towards or away from the center. It's a non-factor. The only thing that actually acts along this center area, the center line, would be the force of tension. So in both cases, the centripetal force is the force of tension.